Alright, so let's go through the Trial 6 2018. So state what is meant by SHM. So this one quite simple. So just means that acceleration is directly proportional to displacement, and of course acceleration and your displacement is always opposite in direction. Yeah, so that is the first part. Okay, the second part we are given AX graph, right? So you can see that the AX graph, right, apparently there's a curvy part here. So the use figure 9.1 to explain how is it known that the mass is oscillating. So it's due to the fact that there's a negative gradient. Also, of course, negative gradient, right, means that the acceleration and displacement is opposite in direction. So meaning, for example, right, at this particular amplitude, so it's a positive displacement. But since the spring is being stretched, so we know that the spring force is towards the left hand side, which is towards the equilibrium. So likewise, as I go to the next equilibrium, the next amplitude, which is here, so you can see that the spring is being compressed, so means that the acceleration is towards the right hand side, and of course the displacement is negative. So you can always notice one thing is that the acceleration is always directed towards the equilibrium, meaning that this mass is actually oscillating about the equilibrium. So you just say, oh, the negative gradient, because you must use figure 9.1. So negative gradient so means that acceleration is directed towards the equilibrium, which means that it's oscillating about the equilibrium. Okay, so let's go to the number 2. Explain why the oscillation is not SHM. So if you look at the graph, there's a curvy part right here. So this tells me that the acceleration and the displacement is not directly proportional. So that's why it's not SHM. So just say that, because the graph is not linear. Hence, acceleration and displacement is not directly proportional. So that's the second part. So of course, remember, must use the figure 9.1, or let's just say they give you a formula, must also use the formula to explain why. Okay, so let's move on to the next part, part B, right? We have this horizontal plate attached to an oscillator. So of course some sand is being sprinkled on it. The plate is made to oscillate vertically with small amplitude at a frequency of 13 Hz. So the oscillation is SHM, right? So I increase the amplitude such that the sand first lose contact with the surface of the plate. So first part, for the plate, as the sand first loses contact with the plate, right, what should be the position of the plate? So must be the maximum displacement about the equilibrium. Meaning, for example, I draw the 3 lines. So this part and this part is the maximum and minimum point. This part right here is the equilibrium. So as the plate, right, is moving down from the amplitude, moving down towards your equilibrium, the sand will first lose contact with the plate. So that is what I meant by the very first part. Okay, of course we are asked to calculate what should be the amplitude of the oscillation such that the sand will first lose contact. This one's simple because as long as you understand one thing is that the sand and the plate, so if they are moving downward in the same direction, so for example, the plate is moving at an acceleration of 9.81. So likewise, the sand, right, is moving at an acceleration of 9.81. This is the first time that the sand will actually lose contact with the plate because they have the same acceleration. So if they have the same acceleration, right, means that there shouldn't be any contact force or normal contact force acting on the sand. Yeah, so the acceleration will be 9.81, and of course I want to determine your x0, which is the amplitude. So my omega squared, so is 2 pi times 13, or 2 pi f. So our f is 13 Hz, you square it. So my x0 is about 9.81 divided by 2 pi 13 square. So it's about, give or take, 0.001470356 meter. This one is meter, right? But you look at the unit is mm, so means that it's about into 1.47 mm. So the amplitude should be 1.47 mm. Okay, so let's move on to part 2. The sand consists of small grain, right? And of course, the sand is being replaced by larger pebble. Suggest explain whether for the pebble to lose contact with the plate, the minimum amplitude of the oscillation would be different. So this one should be no, because remember, for the amplitude, right? So the amplitude is actually equal to A over omega square. So the amplitude, the so-called minimum amplitude, right, only depends on this thing and this thing, which is the acceleration of the oscillator and the angular frequency of the oscillator, not dependent on the size and not dependent on the mass of the pebble. So that is for part 2. Okay, let's move on to part C, the calculation. So a spring hang vertically, right, from a fixed point. So of course 1.2 kg. The mass undergo vertical oscillation with a frequency of 2.5 Hz and amplitude 3.4 cm. So determine the total energy of the oscillation. So this one simple, just quote the formula half m omega square x naught square. So you do the calculation, hopefully you get about 0.171 joules. You can also put in terms of standard formula, 1.71 times 10 negative 1 or times 10 negative 1 joules also can. Okay, so that is for first part. Okay, what about the second part? Second part more challenging. What should be the displacement at which the potential energy and the kinetic energy of the oscillation are equal? So if I sketch the graph, for example, I sketch the energy against the displacement. So definitely, right, my kinetic energy is set phase. Then my PE, my potential energy, is a happy phase. So right here. So like that. So you can see that at 2 points, so at this point and at this point, the kinetic energy and the potential energy is the same. So they actually want us to determine what is the so-called displacement from the equilibrium. So how do I do that? Okay, that's where you need to write down the equation. So for PE, right, we know that the general equation is half m omega square x square. So x is the displacement from the equilibrium. Then for the kinetic energy, so the kinetic energy, the so-called formula will be half m omega square, and then of course x naught square minus x square. So this is the so-called general formula. So you equate them together. So it's like finding your mat. You're using your maths, right? You want to find the intersection between two curves or two graphs, right? You put their equation together or sub their equation together. Then you solve for x. So meaning that you will get half m omega square x square. You equate, this one is a PE. Then equate with half m omega square. So I do the expansion. X naught square minus half m omega square x square. So you just move this whole thing to the very left hand side. So you do the mental calculation. Half plus half 1, right? M omega square x square equal to half m omega square x naught square. So you can do a bit of calculation, a bit of cancellation. So m cancel, omega square cancel. So you can see that x square, right, is actually equal to half x naught square. So you just solve for x. You just solve for your x. So meaning that x square is equal to half of x naught square. So you just square root. So you'll get x equal to 1 over square root 2 x naught. So just, of course, we know our x naught, right? Our x naught is the amplitude to be your 3.4 centimeter. So you just sub in. So 3.4. So 1 over square root 2 times 3.4 is about 2.4 like that. 2.40 centimeter. So this point is 2.4 and this point is negative 2.4. So this will be the answer, 2.40 centimeter. Okay, let's move on to the very last part. The last part is sketching of the graph. So we are asked to sketch your total energy, the kinetic energy, and the potential energy. How do I do that? And you look at the number of marks, is 6 marks. So cannot be so easy, right? So of course, the general shape, I think you all know. So for example, you can see that the orange graph, right, is your kinetic energy. The red color graph, don't need to say, is your total energy. The black color graph is your potential energy. So these are something like your horizontal SHM like that. Okay, then you must label all the parts. So this one is the maximum KE, right? And then this one is the maximum PE. And of course, last but not least, important thing to take note is actually this part, the intersection. So when you intersect at about 2.4 or 2.4, we must ensure one thing is that they must have the same energy. So you do a bit of side calculation, right? Or behind the envelope calculation, you notice that when they have the same energy is about 0.085 like that. So 0.085 I just annotate here due to the skill. My skill not very good. So you all can have a better skill, just draw a better skill. So at this point, right, my energy, my so-called KE is 0.085. So likewise, for my PE is also 0.085. So they must intersect at negative 2.4 and positive 2.4. So the shape, everything, the intersection must correspond to one another. So that is how you get the 6 marks credit. So that's all for this part.